crop simulation model. Sir is PhD from US Harvard, and immediately after PhD he joined the university services. And then Sir went abroad for advanced training and research to China for a couple of years, then UK for 1 year as postdoctoral research with Royal Society of London Fellowship, and then he went to Denmark for 3 years as project researcher with Danish government funding, and then later to US for 2 years with funding from NSF USA. He has published more than 75 scientific papers in high-impact international national journals and traveled some 20 countries in North and South America, Europe, Africa, and Australia. At present, Sir is heading the Department of Agriculture and Metrology at University of Agriculture, Science and Technology, Dharwad, Karnataka. He has led more than 20 externally funded projects with a tune of 50 crores and now leading projects funded by India Meteorological Department. Sir is also Nodal Officer of Gramin Krishi Mausam Seva and Fasal projects. And he's having one project from ISRO as well. Dr. Sir is also a life member to several professional societies and besides being a member to several international organizations. Sir, now stage is yours, sir. Please, you start your presentation.
Thank you. Thank you very much. Good afternoon, good evening, and maybe good morning to some of you from across the globe. I'm very happy to be joining you on this 10 days long online training program. And if there is any delay or lag in communication, the voice reaching you, just be patient. Sometimes internet, poor connection or low connection, we get interrupted, but I will continue. And if you have any questions, please put them in the chat box. So I will take them at the end of my lecture. So today I'm going to talk about the crop weather relationships in very brief, and then using crop simulation models to study how crops respond and how we develop adaptation strategies for the climate risks. So when we talk about crop weather relationship, we refer to two variables. One is a plant, another is a crop. So plant, when you say it's a very voluntary or cultivated plant, which produces a purpose, whereas a crop is a group of the same kind of plant grown on a large scale, on a paddock, on a field, and for some economic purpose, food, fiber, fodder, or any other economic benefit or purpose. But this response, growth, development, and performance of this plant as an individual or crop as a whole very much is influenced by climatic and weather factors. That's why there's a greater need to understand, in fact, better understand crop weather relations. So when we talk about weather and climate, and we use and treat both of them same, but technically they are obviously different. Weather refers to the atmospheric conditions like temperature, pressure, humidity, wind at a particular time and place. And it always refers to the short period of time. Whereas climate, it's an average weather conditions of an area, average, when I say average, it's average for a long period of time. So you can say tropical, subtropical, humid climate of a particular location. But if you zoom in and break down that particular season, have different weather systems. So of course, climate at a global scale, at a regional scale, at a zonal scale is very much affected by both abiotic and biotic factors. We all know that as a basic concept: latitude, altitude, ocean currents, topography, solar radiation, evaporation happening from that locality, orbital variations of the Earth, then volcanic activities around there, and the vegetation. Vegetation comes under biotic, and all these are abiotic. When it comes to biotic, it's a transpiration from the vegetation, respiration, photosynthetic process, decomposition, digestion. All these influence the climate of that particular location. Whereas the weather, in particular, is influenced by temperature, humidity, precipitation, or rain, air pressure, wind, and cloud layer. So obviously, climate and weather are not the same. So as I said just a while ago, weather refers to a very short term and for a very limited area, and it changes rapidly. So hence it's difficult, relatively difficult to predict accurately compared to a climate. Whereas the climate is the average of many years or decades. So hence it's a long term, it applies to a wider area, and you experience seasonal changes, and it's always measured over a long period of time. So to give an example, climate decides what kind of crop and cropping systems are followed in a particular location. Maybe, for example, apple in Kashmir, mangoes in Uttar Pradesh, South India, you know. So winter wheat in North India. Then we have maize and other crops in tropical, subtropical climate. So what kind of crops are grown in a particular region very much influenced by climate at that location. Whereas the weather, it influences the performance of a chosen crop of a given season. So that's a major difference when it comes to the agriculture. That's why we have to understand how climate in the long run and weather in a very short season, intra-seasonal period, influences the crop so that we adapt ourselves for the changing climatic situations. So weather has so much complex relation. It has so many factors: temperature, sunshine radiation, rainfall, carbon dioxide, humidity, wind, and they all interplay. They are interconnected and interplay to affect the main process of crop, that is photosynthesis. And it also influences the crop ET. Photosynthetic process and crop evapotranspiration are the two important processes happening in a plant. And that ultimately decides how much water is required by the crop. That in turn decides how much biomass or yield is produced by the crop. So water availability, soil and management practice on the other side, how much water is available either through the irrigation or through the natural rain, they all meet out the crop demand. And depending on the excess, optimum, deficit, you have the response of crop in terms of yield. So just to go over brief, one of the important factors is light. So when you talk about light, we always talk about photosynthetically active radiation, PAR, which has a direct influence on the how much biomass a plant produces. And when we talk about different crops, we have C3 crops, C4 crops, CAM crops, and among the C3 you have cereals, legumes. They all have a different response to the photosynthetically active radiation. So we need to understand species by species, even coming down to the cultivar or genotype by genotype, how they respond to change in PAR. How does it influence the biomass? Similarly, the same way, how the photosynthetic process changes, with the PAR, and for that matter, irradiance. The relation between photosynthetic active radiation and the net photosynthesis, what you see on the left side figure, is not linear. It's curvilinear. There is a peak of increasing rate, then there's a peak of slowly decreasing rate, then it reaches a maximum or a plateau, then it comes down. Whereas the relation between, the whole canopy photosynthesis and the irradiance, it's always a linear. So we refer to here as a quantum yield, Q, and convexity. That's a measure of efficiency of the photon emission as defined by the ratio between number of photons emitted and the number of photons absorbed. That tells you the relation between net photosynthesis and the photosynthetic active radiation. So similarly, PAR and the CO2 uptake, they are interrelated. What you see in this figure on the x-axis is a photosynthetically active radiation. And on the y-axis, what you see is a net CO2 uptake by the crop. And again, you see the relation. So there is a peak rate and then the slowing rate, then it reaches the maximum. That's the maximum rate of net photosynthesis. And that's what on the x-axis we call it as a light saturation point. Beyond that, any increase in irradiance or PAR has no positive influence on the yield because CO2 uptake or fixation stops there. So this process has to go into the models if models have to accurately predict crop response to the weather. Second factor, temperature. When you talk about temperature, it's the air temperature. All biological and chemical processes taking place on this soil or above here are all connected to the air temperature. There are certain relations. And when we talk about crops, agriculture crops, we refer to cardinal temperature. So all plants have like maximum temperature, optimum temperature, and minimum limits of temperature. And the limits are cardinal temperature points and the optimum temperature range, it's very important for a crop. Otherwise, we never exploit the potential yield. So when you talk about those cardinal temperature, we generally, especially in the field of crop simulation modeling, we refer to these four different types, limits of temperature. One is a base temperature, or rather we call it as a T base. It's a temperature below which there is no growth. So it's like a dead, or maybe a plant in a coma. Then you have a next cardinal temperature or limit of temperature, that is T minimum. This is the temperature where crop growth takes place, but in a very decreasing rate or very minimal rate, just for its survival. You don't you don't see the appreciable quantity of biomass accumulation on a daily basis. So maximum temperature, Tmax, is where above which the growth ceases or sometimes leads to damaging the crop and plants might die. And the optimum temperature is between T minimum and T maximum, at which the rate of metabolic processes are at their maximum. That's what the plants love to achieve their potential yield. And all our management strategies should be to make sure that crop is exposed to this optimum temperature. That means choice of crop for a given location of climate or weather should be in such a way that crop gets optimum temperature during all its critical phases or stages all through the growing season. Only then we can go closer to the potential yield of the crop. When you look at the temperature and crop response, every process of activities, respiration, photosynthesis, its overall growth rate, they all have a different relation with the temperature. As the temperature increases, most of the processes, most of these physiological processes in the body of the plant, they start increasing. Then they reach the peak. Then they start declining. That means for every process, we have a minimum temperature, we have a maximum temperature, then we have an optimum range. The same I explained in another example. Yeah, this is how. You might see this sigmoid or a bell curve type of response in most of the crops, but no two responses of two different crops match the same. They are slightly
Excuse
different.
me, sir. Hello?
Yeah. Yeah, please.
Sir, your camera is off, sir. Sir, can you please open the camera?
Oh, my camera is off.
Sir, video.
Sorry. Yeah, okay.
Yeah. Now it is clear. Thank you, sir. Thank you so much.
Yeah. Was it off all this time?
Yes, sir.
Okay.
Okay.
So this is it's a general response of any crop. You would see base temperature, minimum temperature, then we have optimum 1 and optimum 2. Optimum 1 and optimum 2 means it's a range, range of temperature. In that range, crop is at its maximum activity. Then you have Tmax. So there's temperature in different crops, the relation between temperature and the photosynthetic activity. Different species have different response. And again, that curve changes. The peak curve, the plateau, and the range, they shift. They shift from crop to crop. So to understand crop weather relation, so we have to have a crop specific, species specific, probably the cultivar specific studies to understand that optimum range, so that those optimum parameters are entered into the crop simulation models to simulate and predict the crop response accurately to the given climate and weather. So in this figure, what you see is the temperature on the x-axis and CO2 consumption on the y-axis, and you CO2 levels on the y-axis. You see the response, C3 crops at low CO2 level, C3 or C4 plants at high CO2 level. As the CO2 concentration increases, crop response does change. The same thing, I think I missed a slide anyway. So C3 and C4 crops have a different response to the CO2 levels. I think it comes here. Okay, on the x-axis, what you see here is the CO2 concentration in parts per million. On the y-axis, what you see is the net photosynthetic rate of a plant. And you see the obvious contrasting response of both C3 and C4. So we are somewhere in 400 plus level now. As of now, we are actually, this is a little slight old slide. We are now 410, 415, or maybe close to 418 or 20 ppm. So the response of C4 crops to CO2 enriched CO2 has reached its plateau, in the sense it has reached its maximum capacity. They respond less to CO2 now in the coming decades than C3 crops. When you look at C3 crops, they will continue to respond positively to increasing concentration, going up to 1,000, 1,100. So what do you see? What does this suggest is in future climates, we tend to gain more benefits from the C3 crops in terms of yield with increasing CO2 concentration, but not so with the C4 crops. But they have different advantages, like they withstand drought. They love more irradiation. They love more radiation. So under hot climate conditions or higher temperature conditions of future, projected future, C4 have their own advantage of sustaining that temperature, whereas C3s have an advantage of fixing more CO2. So obviously we need more C3 and C4 crops to continue in our cropping systems in the coming decades as well. So here is just one example of maize as a C4 crop and a bean as a C3 crop. You would see how C4 crop saturation quite early and then it reaches plateau, whereas C3 crops goes up with increase in CO2. Then obvious another important factor of weather that influences crop performance is water. And you know water is involved in two important processes of the plant. One is photosynthesis, another is respiration. So water is a source of electron in photosynthetic process. Thus, it's a reactant in photosynthetic process, and it's a product in respiration. So it acts like both reactant as well as a product. And if I just from here, I jump on to one of the long-term data analysis here, the rainfall, southwest months from June to September for India. This is for India from 1953 to 2009. Almost about 60 years of rainfall data. If you see here, there's a slight reduction in the southwest monsoon rainfall occurring. This is an average for the whole country. Of course, we do have regional changes. Some parts of some regions of India have a trend, some have an even more decreasing trend, and some have hardly any change in the trend. But this is the overall picture for the country as a whole for southwest monsoon, during which we get close to 70-72% of the total annual rainfall. So there is a slight decreasing trend in the southwest monsoon. Probably the rainfall is shifting to the post-rainy season or summer season. So that because there's no obvious change in the total annual rainfall for its own season. And for that season, when you look at different crops here, rice, wheat, coarse cereals, total food grain production, pulses, there is a year-to-year variation. What you see, the humps, the spikes and down, up and down in all the crops, including total food production, do suggest that our India's national or seasonal food production is significantly related, very closely related to the changes in the annual rainfall. As you see the year-to-year variation in the rainfall, so do you see the variation in the year-to-year production of food grain. But overall trend, there is an increasing trend of all the food grain items. That's due to multiple reasons like increasing productivity and mainly productivity per unit area. So when you talk about this water, temperature, radiation, CO2, another factor that comes in here is we call is the Kc factor, because if you're talking about water management in crops, we always refer to the Kc factor. That in turn decides how much evapotranspiration occurs from the plant. And the Kc value changes from stage to stage. That's why when we do modeling, in the field of modeling, crop phenology is very critical. Unless you understand the phenology properly and their duration and phase-wise duration, it's difficult to capture the variation from phase to phase in their response to water demand, in their response to radiation, in their response to CO2, and in their daily metabolic process. Keeping all these, I just went through very briefly all these intricate relations and responses between crop and weather. We do use crop simulation models to understand and apply for agriculture purpose. So why do you use models? We have a lot of problems. We have a lot of problems like any other field of science. We do have a lot of issues in agriculture. And these issues are quite complex because what you saw just in a few slides. There are so many factors influencing independently as well as interconnectedly. So there are multiple factors influencing the crop or the plant. And the same problems exist all over the world. Maybe the rate and extent of that problem changes, but agriculture, when you take agriculture as a whole globally, have the same issues: climatic factors, weather factors, soil factors, management factors, and some extreme events. So the problems are more or less the same. They exist globally, but they are complex. It's only the matter of scale, and it's only a matter of time and uh, space. So upscaling is very much required at regional scale or continental scale. And to study this, all these complex things requires a lot of logistical and human resources, financial resources. Because of their limitation, rather limitation. So we tend to depend more on such automation, automated models. And one such models is crop simulation models. In fact, agriculture, I would say agriculture is the last field of science where models and this automation came quite late. Otherwise, in the field of engineering, in the field of medical, and other disciplines, this modeling, application of models for decision making has been there many, many decades ago. So what is a model? It's a simplified representation of an object or a system or a process. Or you can also call it as a schematic representation of a concept of a system. So what is a crop model? It's a simple representation of a crop. Or if you talk about system, it's a simple representation of a soil ecosystem or soil system. So crop models are the tools research which help in solving the problems related to agriculture or crop production per se. So one of the assumptions of modeling is, I'm referring to the second paragraph here, assumption of modeling is that any given process in a plant or a crop or in an agro-system can be expressed in a formal mathematical statement or maybe a set of statements and put them together, connect them the way they operate in a biosystem and make them work automatically. So you need certain level of inputs for the model to operate. Then you have all these intricate processes placed, connected or interconnected, and they are operated by a user-friendly manager system. Then when you run the model, you get the outputs. What are those kind of inputs? What are the inputs we talk about? Very simplistically, it's about crop. If you are growing a crop, a particular cultivar, its related data. Then land, soil related data, nutrients, water holding capacity, pH, organic matter, profile-wise data. Then you have a weather data, T max, T minimum, solar radiation, humidity, wind, rainfall. Then the crop management data, rain-fed system, irrigated system, application of fertilizer, water, data sowing, spacing, plant population, all those things go in an input. Then the soil management data, the tillage practices one follows. Gives you number of outputs, crop growth and development on a time series, whichever you choose. Maybe daily time step, weekly time step, a monthly. Crop yield and yield-related data, soil moisture dynamics, what happens on a daily time basis, or weekly or monthly, nutrient dynamics, crop water and nutrient uptake, its efficiency, all the outputs will come in. So what exists in the system? The one I show you here, what exists in the middle, input, output, what exists in the processing unit is hundreds of soil and crop related biophysical processes. They are represented in a mathematical equations and they are interlinked as closely as they exist in biophysical system, if not perfectly. Because there is always, trade-off between how complex you want to model, how simple you want to model. We want the model to simulate the crop growth accurately. For that, you need a certain number of mathematical equations. Those processes go into the model, but at the same time, you don't want model to be too complex so that people don't use them. So there is always a trade-off as to how much complexity you want in the model. So why do you use the models as tools? I told you we have so many problems are complex. They exist elsewhere. It's a matter of scale and operation. So there's a logistical, human, and financial constraint all over the world. And there is an advent and advancement in computer technology. So why can't we use that automation and computer technology? Then there is an advances in understanding of these biophysical processes. As the time passes, as we speak, we have a much better understanding of the crop weather relations now through the systematic experiments than 10 years ago, 20 years ago, 30 years ago. So why can't we use the findings into the system and develop a tool, automatic tool, which can help us, in our decision-making process. So when you talk about models, we have different scale of models. Models that can be operated at global scale, models that can be operated at cell or physiological, plant physiological level. But the accuracy and the demand for input changes as the scale changes. If you come down here on the x-axis, you have from hours to years. On the y-axis, you have a plant level to global scale. So if you are in the left-hand bottom corner, you have a physiological models. They need a lot of detailed data, very detailed data, because they are operating at the plant level. They are operating at the molecular or cell level, what is actually happening. To capture those processes, you need a very accurate input data to develop models for that. But as you go up, probably you are given more freedom to have some error in that. So models are applied at all the scales. What now the one in the crop models? They operate on a daily time step and they operate at the field level as a tool for the farmers. The same in another way. Today models are used at all scales. Topmost, the farmer is using the crop models for his management decision making. Farm level, they are being used by the enterprises, the companies, the insurance companies, producers, suppliers. At the ecosystem level, the district, it's done for economic optimization, environmental impact assessment, pollution assessment. Then regional level, state governments, regional agencies are using. At national level, governments are using for food security, safety, strategic planning, import, export, trade policies, different kinds of models. And at global scale, international agencies, multinational companies, they are using the models for international treaties, protocols, projections, predicting the food demand of the next 10, 20, 30 years, population growth, food demand, land change, land use change, and all those things. So what does this crop model is based on? It's basically based on an assumption and the concept that the genetic potential is at one level. What we actually harvest on the farmer field is at another level. And there is a huge gap. And this gap is influenced by different factors. And using the models, we can fill this gap and try to achieve potential yield. So what you see here on the x-axis is one hypothetical yield level of a crop. Say, for example, potato, 20 tons, 20,000 kilograms per hectare means 20 tons of potato per hectare. And on the y-axis, we have three different levels of production. One is the potential production, another is attainable production, and the third one is actual production. So you achieve a 20 tons of potential production when your factors, like those we call it as a defining factor, they define the yield, like carbon dioxide, radiation, temperature, day length, crop characteristics. They are all perfect to achieve that one. No other things influence. But we most often achieve attainable yield because it's limited by certain things. That's why we call it as a limiting factor, like water. We may not, or if it's a rain-fed crop, rain doesn't occur as and when the crop needs, or as and when the farmer needs. So there's always a gap, or lag, or deficiency, or excess of water for a crop. Then we may not apply nutrients as and when the crop requires. There's again a gap. So because of these mismatch between the requirement of water and nutrients for the crop, the yield is limited to a certain extent. Instead of 20 tons, hypothetically say, we harvest only 10 tons. That gap is defined by the limiting factors. Then you have an actual yield. When you look at the individual farmers, some may achieve attainable yield, some, but most of the farmers not achieve attainable yield. They actually harvest actual yield because they are further affected by certain more factors like weeds, pests, diseases. Although the intention of every farmer, every manager is to make sure that there are no weeds, pests, or diseases, but it's hardly possible to control them or manage them. They do influence the crop performance. They extract moisture, nutrients. They take up, they affect the crop growth, their metabolic activities through diseases, infestation. They reduce the photosynthetic activity. So they become reducing factors. So model basically depends on this concept that there are certain defining factors and there are certain limiting factors and there are some reducing factors. So if we partition the role of each of these factors, then we can fill the gap through optimum management using the crop simulation models. So the same is presented here in a visual picture. So what you see on the left side is a healthy, tall soybean crop potential. It's defined by the factors which decide it. There are no other deficiencies. There are no limiting factors, reducing factors playing on it. So you get the maximum yield. But once the limiting factor starts playing on it, you have a reduced growth, reduced pod. So you get only certain amount of yield. That is attainable yield. Then you have other factors playing, which further reduces the crop, maybe through diseases, insects, infestation, or weeds. Then you have a further reduced yield. That is the actual yield. So when you talk about models, there are hundreds of models across the world, hundreds. You can read so many of them. These are AppSim, Infocrop, Sticks, GLAM, Oriza, UFOS, CropSys, AquaCrop, MaxNet, DNDC, Epic, so many. And this, in general, you can say some are big text, some are small text, because the bigger means the most popular models, I would say. DSAT, Stakes, AppSim, Infocrop, Epic, DNDC, GLAM, Oriza, UFOS, CropSys. These are some of the models which have been extensively used across the world by different policymakers, institutions, agencies, and research groups. And some are less popular. So where are the applications? I quickly run through some of the examples done at our location and all, just to give an idea where crop models can be used for understanding the crop response to weather and in helping decision making. One of the challenges of today's the changing climate situation is we obviously need different crops for the coming decade. The varieties and hybrids which are popular now, which may be giving highest yield now, may not be suitable in coming decades because temperature are rising, rainfall patterns are changing. This is affecting the crop cycle. That is going to affect the crop cycle. Warming will increase, the rate of growth and development of the crop. Probably the crop that get harvested in 100 days today, in another 10 to 20 years, maybe may get harvested by 80, 85 days. There will be reduction in the total crop duration. To that extent, the crop yield will be reduced. So it's prime important that we come up with a new types for the future climate well in time so that breeders start working on them and they develop those trait-based cultivars and genotypes of future. In that sense, I rather request, or rather suggest audience here to read some of these papers about how crop simulation models are used to help in developing idiotypes. One is by Rutter and his team, use of crop simulation modeling to aid idiotype design of future cereal cultivars. Another one is Simonov and Statanovic, designing high-yielding wheat idiotypes for a changing climate. And there's another one, designing future barley idiotypes. There are many more, but I'm just giving you a couple of examples here where they have used modeling as a tool to suggest what kind of crops we might need in future climates. Few more examples here. I give one or two practical examples where we use the model at a zonal level. Here one is to identify maize hybrid idiotype for a particular zone in Karnataka state in India. What we did is we considered certain scenarios, different scenarios. As of now, it's 400 plus ppm. Then we considered 450 or 500 ppm. Then different scenarios, the current temperature as of now, 2015 to 2020. Then 1 degree increase, 2 degree increase. We screened 4 different hybrids of the maize for a particular zone on a deep black soils under rain-fed situations. what we did is we played with some of the crop traits. What you see at the bottom is the P1, P2, sorry, P1, P5, G1, G2. There are a certain number of coefficients, and if you are using the models or have heard of models, probably you would understand that every model, every cultivar is defined by certain genetic traits. So those traits will influence how much yield the crop gives. So those traits are put into the model as a certain number. So those numbers, we played with those numbers. The currently what is available is that, and when we changed about 5 to 10%, then we see how far we can compensate the yield loss due to increase in temperature under future climates. So we changed those coefficients. These are the changed ones by 5% and 10%. And we ran them for the current climate, how much yield they are giving, and how much they're going to give in the future climate. What you see here is one example for two hybrids, 3 different levels of CO2 and 3 different temperature levels. One is baseline, another is 1 degree increase, another 2 degree increase. And you would see the difference in the antithesis stage, you would see difference in the maturity stage, then you would also see a change in yield. I'll skip on to the next one. The same thing we did for other hybrids, and we saw what is the percent reduction over baseline. On an average, about 6 to 11, 13% reduction in yield was observed due to increase in temperature by 2 degrees. For every 1 degree increase in temperature, there was a reduction about 6 to 7% in yield for our climate, this particular zone implemented, which again changes from place to place. So we come up with an idiotype. The idiotype that should compensate this yield loss about 6 to 11% for 6 to 7% for every 1 degree increase, and still continue to give higher yield at different CO2 level. So that we could achieve. We could achieve about on an average 9 to 16% increase in the yield if we change these traits by 5 to 10%. Then it's easy. Using the model, we can suggest, okay, change the vegetative phase or grain filling phase, or maybe you can increase the size of the seed. Those traits we can suggest to the breeder. What to find? Vegetative period showed the least positive effect on the yield, only about 0.5% of the yield increased, with a 10% increase in this vegetative period. So for this zone, changing the vegetative period is not a really good idea in coming decades. But increasing the post-flowering period, that from flowering to maturity, if you increase that period by 10%, we found an increase in yield by 12%. That means it's quite sensitive. Then another trait, very important one, is by increasing the number of seeds per plant, probably by increasing the number of seeds per cob, if it's a maize, a year, by 10%, we could achieve an increase in yield by about 16 to 24%. Whereas seed filling rate, somehow our management system, or through the increased harvest index or translocation of photosynthesis from the plant system to the grain, if we could increase that trait by 10%, we can achieve a yield increase by 9%. So this tells you how each trait has an influence on the yield, and which trait we should play with in our crop improvement programs, so that we come up with better idiotypes for the future climate. We did the same for some other hybrids. I would rather skip it. We did for like 30 to 40 different maize hybrids. Some are private, some are public, and we could see, we studied them using the models over a period of 30 years. Now, one of the advantages of using models, you can run and study any system, any crop, any management practices over a long period of time in a computer system, right? If an agronomist or a soil scientist or a geologist had to study and come up with these things, one has to repeat the experiment year after year, year after year, to have some reliable outputs. But if you have a system, automated crop simulation systems, which can run the crop for years together, hundreds of years if possible, if you require, in few minutes, a day or two, with this advent of supercomputers, so it's possible. We could screen about close to 50 hybrids in a year from multiple locations, and we could see the genetic variability among the hybrids, how public hybrids are responding, how private hybrids are responding, and it becomes easy for the farmers to pick and choose the right hybrid. And that tells you how each hybrid, each genotype responds to the particular weather and weather friendly. Then you would see which is more drought tolerant, which is susceptible, which is resistant. And then another example where we can use the crop simulation models to understand and use as a tool in decision making is yield gap analysis. This is very critical. And there are many studies across the world which suggest that if we can fill the gap between the present genetic potential of every variety that is available across the world through better management, we can increase on an average 20 to 30% our national food production of any country. Because there is a gap. That's what the concept of modeling is about. There is a gap between potential yield, attainable yield, and actual yield. And our effort as a priority should be to fill this gap rather than just coming up with the new varieties and cultivars. No matter, it's a good idea to have better yielding varieties, better yielding cultivars, high yielding varieties. But if we continue to have higher yield gap between the actual yield on the field and the potential yield, we'll have a very least advantage of having the new varieties. So we should fill this gap. So models can be used very effectively to quantify the yield gap and participate where this yield gap is coming. Is it due to nutrients? Is it due to mismanagement of water? Is it due to disease? Then we fill those gaps. One example here, we did it for green gram, soybean, chickpea. We quantified the yield gap between potential yield and actual yield. Actual yield is the one under rain-fed situation, and the potential yield is the one with optimum moisture. Crop doesn't experience any moisture conditions. So you would see how different crops have different level of yield gap. The same we did it for maize, sorghum, and wheat. Another example is these days in the farming, because of the technological advantage, farmers tend to grow any crop anywhere. But despite that, crop potential and its yield is very much influenced by the weather of the location, no matter what, because we can't change the weather. We can only change the crop varieties and we can improvise our management, but we cannot manipulate the weather. So weather still, and it is going to, in future also, going to influence the crop and how it performs. So it's always good on the part of manager to identify a suitable area. Which crop is good for which area? Choice of crop for a particular location. This is this can be very easily done using crop simulation modeling. Just an example, we chose North Interior Karnataka, that's about 3 million hectares of area of a Karnataka state, representing 4 districts for a number of crops. And we ranked them. What is the best district in this region to grow a particular crop? Say, for example, green gram. For green gram, we found Dharwad is the best location to grow. Next best is Gadag, next is Bagalkot. I have just given code there. Some of you may not understand what that code stands for. It's a local name. So copper, the least yielding district. If a policymaker at district level or at state level had to decide, they shouldn't recommend green gram as a first choice of crop for this particular district. They should rather suggest green gram is best in these 1, 2, 3 ranked districts. It helps easily. We do the same for maize hybrids. When it comes to maize crop, different district ranked first. Haveri district came first, then came Dharwad. Again, Koppal and Raichur were the leading districts. So choice of a crop for a suitable area can be easily done through our decision system support, that is crop simulation. It becomes easy for the district level and state level to plan crop and cropping system for a particular region. Which district should focus on which crop so that the productivity is increased and the total production of that district and that state or rather region and national level is increased by perfect matching of crop and the climate of the location, rather than giving a choice to the farmer. We did the same for all the different crops: soybean, chickpea, and maize, some more maize hybrids. We also looked at which is the best time to sow a crop. Because as an agronomist, as a farm manager, our job is to sow the crop at optimum time window so that we harvest maximum yield. And it's It's very easy to make this decision using crop simulation models. You could see from June 1st night to August 1st second fortnight. You see a huge difference by delaying the sowing. This is under rain-fed situation. I'm not talking about irrigated situation. When you have a fully irrigated situation, the trend completely reverses. No matter where you grow, the timing would be different. But here under rain-fed situation, we could see 50% reduction in the yield in a matter of about 45 days. So there is this concept still exists in rain-fed situations, optimum sowing window. This has to be found. This has to be found for every crop, every zone, because, and especially in the context of climate change, because of the change in climate and rainfall patterns, we have to re-optimize, look back and re-optimize the sowing windows for every existing variety of that particular location so that we get the maximum yield. This is under irrigated condition for the maize I was telling you. We could sow the crop round the year at weekly interval using crop simulation models. If you have to have an experiment, it's very difficult to have round the year experiment in multiple locations. And you would see which month of the year is the best to realize highest yield. And we could, for our reason, we could see September 1st and 2nd fortnight. September 1st and 2nd fortnight is the best time for an irrigated maize production. But if it's a rain-fed, we obviously say June 1st fortnight because we are dependent on the onset of the monsoon. So decisions do change depending on the available resources in the system, and models can very well be used to make these decisions easy. You could harvest. We found 2 timings in a year for our location for maize hybrids across the hybrid. This is a 45 hybrids, including public and private. You could see if you want to realize highest yield, there is one time you can either sow in October 1st or 2nd fortnight, or you can sow in the April 1st fortnight. It's easy. Is it easy to see? Across districts, both for rain-fed situation, for the current climate, and for the projected climate. And they do change. Irrigated, no much change you can see. 15 July is the best across the district, but under rain-fed, optimum sowing window changes because the occurrence of the rainfall and the continuity of the monsoon in those districts is quite different. Among the districts, it's quite different. But if a farmer has access to water, he doesn't have to worry about anything. Give irrigation, take up a sowing. So there are 2 contrasting situations. Potential situation is different. Rain-fed situations is different. So do our decision making has to be different. We can't blindly say this is the best time to sow. We need to know whether it's an irrigated farmer or rain-fed farmer. Of an rain-fed farmer, which part of the country, which part of the state. Then we have to study when the monsoon goes there, how the monsoon progresses in that part. Then it becomes easy to rank which part is number 1 place for this crop, number 2, number 3, number 4. What you see is just an example on black soils, rain-fed condition, potential condition. Rain-fed and potential. 12 districts of our North Interior Karnataka state in India. And under rain-fed, you have different ranking. This comes first, this comes second, this comes third. But when you have a irrigated condition, the ranking changes. This district comes first. Then we can, if it's irrigated, okay, go for maize in this district. That's the highest. Then probably decision making, where to expand our irrigation system, realize highest yield of the maize. Future climate, it doesn't remain the same. Ranking of the performance of maize hybrid, particular hybrid, you can take another hybrid. So changes under current situation and the future situation. With the change in climate, again the ranking. It's easy. You can foresee in next 10 years, 20 years, 30 years, which district is going to be a potential district to grow a particular crop. So it becomes very easy for the policymakers to plan crops and cropping systems using crop simulation models. And when we did some work on choice of best cropping systems, not just crops, cropping systems. So I would rather skip there. We did that one and quantified the future climate effect on different crops, how much it affects, and when to give irrigation, what are the critical stages, sensitive stages of irrigation, and through the use of crop simulation models. Through this, we could better understand how
Oh, Wes.
Yes, sir.
Okay, I'm trying again. Huh? He's having some issue.
Yeah, yeah. What is it? Mute is the Sir has joined, sir.
Okay, just make him panelist.
Yeah. Okay. Can you guys hear me?
Yes, 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 sir.
Yeah. My laptop ran out of power, so yeah. I just had few more slides, but anyway.
No problem, sir. Please carry on.
Yeah. So I just had to just switch. I thought I had enough there. Okay.
Yes, sir. Sir, please share screen again, sir.
Sure. I will do that. Do that.
Now it's
Yes.
Anyway, do you see my screen now?
Yes, yes, sir.
Yeah.
it's visible now.
Yeah, it's visible. So I was just talking about this anyway. We did the same for soybean. We changed the temperature with the baseline and studied their response. And sensitive. Yeah, I'll just skip that one and go to the next one here. Identifying the sensitive stages and optimizing the timing of limited irrigation resources using crop simulation. Well, we did this for Kharif sorghum and for a particular region in our Karnataka state for two varieties and two hybrids. We skipped the irrigation. This is very much possible with use of crop simulation models. Otherwise, logistically, it's very difficult to skip irrigation in an experiment, field experiment. But we can easily do using the crop simulation models. You have a weather files in the model. In that files, first you basically study how crop phenology goes, at what time it comes to the flowering, at what time it starts setting grain, what time it matures, then noting those dates. And then you can superimpose dry periods coinciding to that period or preceding to that period. And then you can study how crop responds to the dearth of moisture, lack of moisture, or absence of rainfall during that period. So it's very difficult in a field experimentation to simulate variation in the rainfall experimentation. For that, you need a high-end, very expensive logistic like a rainout shelter. Rainout shelters are very expensive to have in every station or every university. But crop simulation models can be very easily used to simulate this absence of rain at a particular period, or quantity of rain at a particular period, increase in rainfall, or increase or decrease in rainy days, rainy events. So all these manipulation can be done. So we did that. And for each date of sowing, what you see here is DOS, different date of sowing, different varieties, different year. We skipped certain amount of rainfall at critical stages, like 2 weeks, no rain prior to panicle initiation, or maybe for 4 weeks prior to panicle initiation, no rain, 2 weeks prior to the end of grain feeding. Why? How we chose this panicle initiation and EGF? It's based on our preliminary study to understanding which stages are most critical for the yield. Then we simulated absence of rain 2 weeks and 4 weeks prior to those critical stages. And we saw how the yield is affected. So across data sowing and across different varieties and hybrids. This could be replicated for any number of crops, any location. Then it becomes very easy for us to understand, how to use the limited resources, be it nutrients and water, to realize maximum yield in a crop. So this is, crop simulation models help you better understand how crop respond to the climatic conditions and weather parameters. Then how to manage. We did the same for chickpea, skipping rains at different stages, rain fed, free sowing, skipping one irrigation at first flowering, skipping first forward, rain filling. Then we see the gain in yield by giving that additional irrigation at these grids, anywhere between 10 to 28%. Then it becomes easy for farmer to know if a farmer has an access for one additional irrigation, drain filling is the best stage. He can realize about 28 to 29% increase in the yield instead of giving elsewhere. Second best, pre-sowing irrigation is the best. Third best, irrigation at first part. And giving irrigation at the flowering stage gave the least response in the yield. So these responses between crop and weather conditions help us make a good decision. And apart from this, there are many applications of crop simulation models.
Wes, please unmute the participant.
Okay. So apart from these, many more applications are there of crop simulation models which can be very well used in different aspects. Like, for example, development of improved understanding of the structure, process, function of crop systems and productivity forecasting. Developing adaptation to climate and climate change. This is happening all over the world. Initially, although crop simulation models came into existence to operate at the field level, at product level, but with the advent of new science and incorporating those processes into models, they are now being used at every scale, more so in policymaking at the regional level, continental level, national and international level. And it helps in adapting, developing adaptations to those climate and climate change situations. Of course, identifying traits of future and next crop generations through estimation of potential yields, yield gaps, yield forecasting. We've been doing using the satellite images as well as cross simulation models in yield forecasting, and with this we can do the advanced forecasting before the harvest of the crop. That helps at government level, policymakers and trade in trading and import and export activities. So with the crop simulation models, we can model study G by E by M interactions, how the genetics interacts with the environment and management, and environmental impact assessment, economic assessments, sustainability assessments, and there are many more factors. So just to conclude, crop simulation models, at least in the last 3-4 decades, and their work across the world shows that they can very well be used to study and quantify crop weather relation and their responses at a number of scales, local level, regional level, continental scale, to study or to assess crops, cropping systems, soil, water, nutrient dynamics, and in optimizing input resources. Of course, after thorough calibration and validation of the models. And with that, I conclude my lecture and take up questions if you have any. Thank you.
Thank you very much. Thank you very much, sir, for a nice lecture. So we have
Thank you.
questions in this box. So I will ask you one by one. The first question is from Dr. Nimra Aryan. How much of the dependency of different input variable matters in mathematical model?
Okay, if you take inputs, I would make a list of seed rate, plant population, nutrient that takes into account all kind of nutrients, especially nitrogen, phosphorus, and then water. These are the five important inputs, and they are very much taken care in the model, especially the model I'm referring to, SAT, AFSIM, and all those major models. They are taken into account, how exactly they operate in a biological system, biophysical system. The same relations are being incorporated to a great extent, okay, into the model. But there are limitations as to, if I give one example of water, how the water is taken into account in the model. While the water flows in the soil profile, both vertically as well as sideways. However, most of the models are still treating water movement only the vertical way in a soil profile. So there are certain limitations, but to a great extent, for example, if I give another example, this is nitrogen. In nitrogen, nitrification process, denitrification process, the transformation relations, and the possibility of release of greenhouse gases or nitrous oxide in the process of this transformation are being quantified very much into the model. Then runoff is taken into account. For that, slope of the soil, color of the soil, then texture of the soil are taken into account. Based on that, model simulates, based on the intensity of the rain across time, it simulates how much rain would go into the infiltration as an infiltration process, how much will go out as a runoff. So that is taken into account.
Okay. Thank you, sir. Sir, one more question from Paramesh V. Whether increase in carbon dioxide concentration will increase crop yield in C3 or C4? The recent meta-analysis of FACE experiment shown reduced specific leaf area and stomatal conductance under elevated carbon dioxide. Please enlighten us about this issue.
Yes, yeah, I just showed you initially one graphical representation of the general response between C3 and C4. C4 crops, as we all understand, have reached saturation. They are not going to respond positively to any more increase in the CO2. 400 plus ppm scenario, C4 crops will not respond to CO2. But on the contrary, they do respond to increased irradiance, increased radiation, and increased temperature because C4 are more drought tolerant than the C3. So there is an interaction there. So it's not just CO2. And when it comes to C3, C3 crops would continue to respond with increase in CO2 levels. And most of the studies, lab studies, growth chamber studies, haven't shown any saturation that C3 crop are going to achieve until at least 1000 ppm, 1100 ppm. But the increment is quite nominal, very nominal, but there is a positive increment in C3 crops. With regard to how increased CO2 affects specific leaf area and its stomatal behavior, I haven't read many papers in recent past. That's is obvious, may be possible. It's another dimension of the work. So then again, so that's why this growth chamber and lab-based systematic studies should continue to better understand even more details how crops respond to increased CO2 or increased temperature and their interaction. What the audience, the participant suggesting would be quite possible, but I am not aware of that paper or that work.
Okay, thank you, sir. Sir, one more question from Dr. Naveen. In DSAT version crop simulation model need to many parameters for forecasting yield. How to minimize the data set for high accuracy forecasting?
Oh yeah, during my lecture I talked about trade-off, trade-off between how much data you want and how much accuracy you target. They are they are very much strongly correlated. If you want high accuracy, you need a high quality data set, and for multiple years, multiple locations, a large number of data set. Only then your calibration and validation will be very optimum, and whatever optimized parameters you achieve after that process would be more robust to work for your location. So minimum data set, we do have a concept of minimum data set, but it's a compromised data set. With a minimum data set, you cannot achieve high accuracy. So for example, if you say minimum data set is the one with which we can successfully run a model for your purpose. But the question is, what is the accuracy level of that model output? So if you could achieve about 80% with MDS, minimum data set, that is acceptable for field management level. As an agronomist, as a farm manager, 80% accuracy is good enough. But if you have a quality data and a large number of data sets, then we can go up to 90+ % in accuracy. So data, quality data and quantity as well is very much required for uh, achieving higher accuracy of the models.
Sir, one more question. It's indigenous from your own university. Soman Gowda B.
Mhm.
Patil. Is
Yes.
crop simulation modeling a game changer for agriculture sustainability and climate change? If yes, how we can achieve sustainability and what up to what extent?
Mm. Now, I wouldn't give that much credit to the crop simulation models or modelers. There will be one of the tools among the rest of the tools we have, like experimentation, lab-based growth chambers, statistical models, and even the own professional expertise to foresee the things through our experience. I would say crop simulations are very handy, very effective tools to support our effort of agronomists, geologists, farm managers, soil scientists, breeders, to help us understand crop weather relations better and foresee into the future and manage well in time, adapt well in time. So not a really the lone game changer, but obviously very important tool to achieve sustainability in coming decades.
So we'll stop here. Thank you very much. The rest questions will email you because we have a remote lecture at 6 from Jared.
Okay, okay.
Separate program, but we will include these participants if they are interested. Thank you
Sure.
very much, sir, sparing your very valuable time.
Thank you.
Today's holiday, and you still give your half time to us. So thank you
Thank
on
you.
behalf
No
of.
problem.
So
Thank
now
you very much.
we'll
Thank you.
have one group photograph. So please, sir,
Sure.
stop your screen sharing. So we'll have group photograph.
Yeah, yeah, yeah.
Participants, please open the cameras. Once this COVID will over, sir, we'll call you. We will invite you to Kashmir
Sure, sure,
for a lecture.
sure, sure.
Wes,
हाँ जी सर.
group photograph, please.
Yeah, yeah.
Oh, okay. Also, started. Sir, please request everyone to open the cameras because some have not yet opened their cameras.
You started.
Next, please.
Is it done?
Yes,
Hey,
sir.
yes, sir. We're done.
Okay. Thank you very much, sir. Thank you once again.
Thank you. Thank you all.
Thank you very much. Thank you. So this is for the information participants that tomorrow we are having a lecture at 6 by Dr. Malasala Murli Nageshwara Rao. He is at University Corporation for Atmospheric Research and visiting scientist at National Oceanic and Atmospheric Administration NOAA Center for Weather and Climate Prediction USA. So right now at 6 we're having one more from Jared Hogenboom, who is the developer of DSAT. So those who are interested, I have already shared a link in WhatsApp group. They can join us at 6. Thank you very much. Thank you. Thank you, sir. Bye-bye.
Okay.